this is the complex beam problem. This is way more difficult than the first one that I did, but the steps are going to be exactly the same, which is why it's very effective to do the other one first. And to begin with, I need to draw this free body diagram so that I have something to work with and something to go off of. So I am going to do that on this piece of paper and make sure that I know all the numbers. I might have to flip back and forth a couple of times, but my free body diagram would look something like this. This beam is 20 feet from the beginning all the way over to this side. It's 20 feet. I do have a reaction force, or a force A. I do have a reaction force, or a force B. I do have a point load on this one, and that point load is 4,000 pounds. And that 4,000 pounds is right at the 6-foot mark. And I also have a uniform load going across the beam of 650 pounds per foot. 650 pounds per foot. So I have a whole bunch of little arrows going across. There would be 20 of them. I am not going to count them all out. I'm just going to draw them on there and pretend that there's 20 of them. But there should be 20 of them going all the way across that beam. Each one of them is worth 650 pounds. So, step number 1, sum all the forces in the x direction, and that is 0. There are no forces acting in the x direction, so I am good. I need to sum all of the forces in the y direction, and it has to be equal to 0. So I have force A, which is acting up, so it is positive. I have force B, which is acting up, so that it is positive. I am going to add a negative 4,000 pounds. And the reason I did it that way is because this symbol means that I'm adding. So I'm adding A and B and the 4,000 pounds. But the 4,000 pounds is acting down. So it's a negative number. And I'm going to add to that all of these little forces, which would be 650 pounds per foot times 20 feet. And that number has to be negative, because all of those together are going to be acting down. So I'm going to pause the video, do a little calculation. Force A plus force B plus negative 4,000, because it acts down, plus negative 13,000, which is those two multiplied together, should equal 0. So if I take these two numbers and add them together, it would be negative 17,000 pounds. And I am going to add that to force B, and I'm going to add that to force A, and that should be equal to 0. So 17,000 pounds equals force A plus force B. At this point, I can't go any further because I have two unknowns. I cannot just simply whack this in half and say half of the force goes to A and half of it goes to B, because there's this 4,000 pounds that's not in the center. If the 4,000 pounds were in the center, that would work. But A is clearly going to have to be supporting more than B is, because the 4,000 pounds is closer to it. So I do need to continue to do this the way that I did the last problem. I can't kind of try to rationalize in my head. And I'm going to summarize around point A. So this is going to be my pivot point. And when I sum all of the moments, it has to be equal to 0. So, force A is at 0 feet. And I'm going to add to that force B, which is at 20 feet. And I am going to add to that negative 4,000 pounds, which is at 6 feet. Because the 4,000 pounds is right at the 6-foot mark. And I am going to add to that 13,000 pounds, negative 13,000 pounds, and that load is uniform. That comes from my uniform load, so I'm going to assume it's going right through the middle of the beam, or the 10-foot mark. And that's where all those numbers came from. I'm going to hit pause, do a little bit of calculating. I am all done calculating, so this is going to drop out because any number times 0 is 0, so I've eliminated a variable. Force B is still here because I can't do anything with that. I don't know what B is. But when I multiply these two numbers together, I get negative 24,000 foot-pounds. That's a torque. And I got to add to that negative 130,000 pound-feet. And that's a negative number because it's acting down. This is a negative number because it's acting down. So I'm just going to do some more simplification behind the scenes here. So B is still B, it's right here. And when I add these two negative numbers together, I get this one. Continuing my simplification, I can add 154,000 pound-feet to both sides. And that is equal to force B times 20 feet. And at this point I can solve for B, divide by 20 feet. Divide this side by 20 feet. The feet are going to cancel. 20 and feet are going to cancel. So when I divide by 20, I get 7700 pounds is equal to force B. Which is nice because now I can come back up here and I can say that force B is equal to 7700 pounds. And if force B is equal to 7700 pounds, force A must be 9300 pounds. And that's what we said. Based on the fact that there's this 4,000 pound load closer to A is going to have to carry more of the load than B is. So if I page through now in the PowerPoint calculation, like this is exactly what's in the Project Lead the Way PowerPoint that you can look at any point in time. But if I go through it, it should make more sense now. Here's the first thing they're doing is they're summing the forces in the x direction, which is 0, because there were no forces to the left or to the right. Now they're summing all the forces that are up and down, A plus B plus negative 4,000 plus negative 650 times 20. This is exactly what I did on my paper. But now that you see it, the numbers should make more sense overall. The next slide is where they're summing the moment around point A. It's easiest to do point A because then it drops out. And this is where they figured out that force B was 7,700 pounds. Going back, you can do some very simple mathematics now to find out what A is. And you are now ready to do your shear diagram. So the shear diagram on graph paper would be really hard at this point because there's this load here. So basically what's happening is they put some key numbers in. When you're doing a shear diagram, it starts at 9,300 because that was A. So A is right here, starting at 9,300. It ends at B, which is 7,700, but that's negative. So from here, it's very uniform load. If I go up to here, from here all the way over, it's just uniform load. From here to that point, from here to the point, dot, 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 it gets to the point, and then it drops 4,000 pounds right there. So this is 650, 650, 650, and then right there is where it drops 4,000 pounds. Every foot, it loses 650 until it gets right there. And then it drops 4,000 pounds, and then continues 650, 650, 650, 650, 650. So this beam does not break right in the middle. The middle's right here. This beam would break over here at that foot mark. And I think, what do we got here? A box is 2 feet. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So this is 2, 4, 6, 8. And I can't tell on the thing if it goes right at 8 or if it's a little bit past this. But if you want to find out what the torque is at that moment, the max moment, the place where the beam would break, we find the area under the curve. So I am not going to do this crazy stuff they do here. That's way too much. The easiest way to find the max moment is to do the area under the curve. There are 3 shapes here: a triangle, and a rectangle. There are 3 shapes. So to find the area of a triangle, it's 1/2 base times height. The height of this triangle is 3,900 pounds. because it goes over every foot until you get to the 6 foot mark. It loses 650 pounds. So that's what they're doing right here. They said, okay, so the pounds, 3,900 because it's 6 feet times 650. The height of that was the length of it was 6 feet because that's where the point source was at 6 feet. And 1/2 base times height. This B is simple. That's just base times height. So that's 5,400 high, because 93 minus 39, 5,400 high. And it's 6 feet across. If this was 6 feet across, this is still 6 feet across. And over here, it looks like that wasn't exactly 2 feet. It was like 2.15. But you take that 2.15 times 1,400, and the reason you have 1,400 left is after you drop the 4,000, that's what's left. Add all those up, and that's your max moment. In a couple days, I am going to show you a little bit easier way to get the max moment, so if you're stressing on that, don't worry about it too much. And when you're doing your calculations for beam 1 and beam 2, the area under the curve is going to be very simple for both of those. The area under the curve, super simple for both of them, so don't stress too much about that. So we've now done a complex beam problem, a simple beam problem, and the math was exactly the same. The only thing that was harder here was figuring out that max moment, and like I said, in a couple days we're going to make that easier anyhow. So don't stress too much about it. You do now have enough information that you can do problem 1 and problem 2. You can find both of them in the red homework folder. Good luck, and I will see you in the next class.